for H. That's the hard way to go. Thing to do would be to input an H and solve for F. Do you like the F? No, change the H. That calculation is direct. You stick an H in, look, you stick an H in here, stick an H in here, you get A and B immediately, and so forth. So that is an application of packed columns, which is not uncommon. Now, there's another one that's a little bit like this. Here's what it is. You are running a reaction, and let's say it's a liquid phase reaction. So here you are. This is you. You're running a reaction. Here's your reactor. It's a liquid phase reaction. Maybe A is going to B is going to C. You want to make B. You want B. And the way you make this reaction go is you dissolve a homogeneous catalyst in the input. So here comes the input stream. Maybe it's pure A. You dissolve a homogeneous catalyst in here. Now you may have to design a column over here. So this could be a column when you actually do the dissolving of the homogeneous catalyst in the pure A bed. Now you got to be a little bit careful because as soon as you put the homogeneous catalyst in, the reaction probably starts. The reaction that goes on in this reactor is A goes to B, goes to C, out it comes. You want B. Comes out, you want B. So what do you got to do? You got to stop the reaction. So one way to stop the reaction is to get rid of the homogeneous catalyst. So we have a column over here. And out in my garage, I've got this column. And it is some height. Z equals 0, Z equals H. Got to run this liquid in up here. And X and Y will stand for the mole fractions of the homogeneous catalyst. So I'm going to treat this. So in comes X in. That's the mole fraction of the homogeneous catalyst. It's coming in at a flow rate L. That's the flow of this stuff coming out of the reactor. I'm going to treat this with gas like air, where there is no homogeneous catalyst. Y in equals 0. It goes up, and Y out goes out, and X out goes out. So here's the issue. The issue is that you would like to remove a fraction of that catalyst in a certain time. Can I remove a fraction F of catalyst in a time t? You can't let this reaction go on for very long, so this time t is liable to be kind of short. So I keep this catalyst. Maybe I want to remove 95% of this catalyst in 2 seconds or something like that. That might be my job. I've got this column sitting here with an H, and I probably know an HOY for it. And I'm going to try and decide whether I can do this or not, or whether I have to change something to make this work. So all of a sudden, for the first time, I'm interested in what's going on inside the column. I need to know what is going on inside the column. So I'm going to have to write an equation for what's going on inside the column, but first I know what's going on around the column because we've been doing that problem for a long time. So in this case, what kinds of stuff am I going to use? I'm going to make material balances, of course, and write my usual equations. So with yn equals 0, so with yn equals 0, I'll make a balance around the bottom here, and I'll find out that y out must be y in is 0, y out, so it must be L over V x in minus x out. I guess that's right. Yeah, you can see it's right. You've done this enough that you know when you look at equations like this, if the signs are right, the outs have to have the same sign on the same side. So that looks right. So what's going on in my column? Well, what's going on in my column is something like this. Log m x in minus y out over m x out. I like it. I probably don't want to write it like that. I'll write it like that. So what is this going to be? This is going to be e to the mv over L minus 1 h over h of y. So that's what my column's sitting here doing. Now, what is that I don't like about this? I like everything about this. Here are two equations. I can put it for y out. This. I have an equation in x out. I solve for x out. So I know what's coming out of the bottom of my column. I get x out. Now, at this point I've got to decide whether to go on. I haven't done the problem yet, but I can tell whether I failed or not. So what I do when I get to this point is I say, hey, no matter how much time it took in the column, let me look at the value of x out. And let me compare that to 1 minus f x in. If x out is greater than 1 minus f x in, it fails. We can answer the question now. We can't do this problem. So let us say, okay, what we do is we go to x out, and we learn that x out is less than 1 minus f x in. That tells me that 1 minus f x in occurs somewhere in the column before it comes out. So here I fail. Here I say, well, goodness, 1 minus f x in is somewhere in my column. Okay, so I say, gee, the thing to do is to find out where in the column it is. So I'm going to try and find out where in the column it is. Okay, so now I'm not going to integrate my equations from z equal to 0 to z equal to h. I'm going to integrate my equations from z equal to 0 up to some value of z, which I might just call zf. That will be z, where the 1 minus f x in holds. So let me see what I'm going to do. I'm going to write down a companion to that equation, a companion to this equation, which was for the whole column, I'll now write an equation for what's going on right here in terms of y in and x out. And of course, that's easy enough to do. Mx minus y over mx out, given that yn is 0, equals e to the mv over L minus 1 z over h o y. And y is L over v. I guess it's L over v x minus x out. Now, when I was over there, I had the value of x out. And in the case where x out was still greater than what I wanted it to be, I failed. In the case where x out is less than what I really needed to do, I know this concentration is going to appear in the column somewhere. I would like to know where. So I know the value of x out. I know the value of x out. And this then is an equation. Okay, I can put this y in here. This is an equation for x versus z. So this equation here becomes x versus z. So I now know x everywhere in my column for any z I'm interested in between 0 and h. Okay, so, but I'm interested in where z is what we might call zf. So I'll set x equal to 1 minus fx in. That is to say, I'll put x equal to 1 minus fx in, solve for z, and that'll be zf. So here I am with knowing where in the column I met my condition. Am I through? No. I need to know at what time that happened, because what has been specified is I need to have that happen. I need to have x equal to 1 minus f x in, which occurs at zf. I need to have that happen in a specified time, which we'll call t. So what's my question? My question is, how much time does it take for the fluid in the column to get from the top down to zf? Well, that's not a hard calculation to make. I have, again, epsilon's what it was before. So I have epsilon A H minus ZF divided by the molar density of the liquid divided by L. This is the time. Time I am at ZF. So I take this time, compare it to t. That time gets compared to t, and if that time is less than t, I can do the job. If it's not, I can't do the job. So that's how these arguments work. So I can do a lot of interesting problems along those lines. So I want to now turn to a simple model for deciding what heat effects are doing. So let us talk a little bit about what heat effects are doing. And remember that we never had a heat effect problem in distillation because we were always willing to assume that the flows, so in distillation, the heat effects were determining the flows. In packed columns like this, the heat effects are determining solubilities. So, in our packed column, heat effects determine solubilities. So here's what the problem is. Question? No? Here's my problem. I could be doing one of two things. I could be bringing in a liquid, and I could be bringing in a vapor, and I could be stripping solute out of the liquid. Okay, suppose I'm doing that. Now, we've done this problem isothermally. When I strip this solute out of the liquid, there's a heat of vaporization that needs to be supplied. So there's a heat of vaporization, and that comes from the liquid. So the heat to vaporize the solute comes from the liquid. That being the case, the liquid cools. So therefore, the liquid cools as it gives up sensible heat to vaporize the solute. As the liquid cools, what happens? The solubility increases. And as I go down my column with the liquid getting colder and colder, the solubility becomes larger and larger, makes it harder and harder to strip out. So the heat is hurting me when I'm stripping solute out of the liquid. So heat effects here hurt. Heat effects hurt. Now, I could, on the other hand, be doing the other problem. The other problem is I bring a solute in the gas. I'm going to absorb it into the liquid. So here I come. I bring the solute in here. This is the gas. The solute's going this way. I'm trying to pick it up in the liquid. Solute condenses in the liquid. Heat's released. What does the heat do? So here, the solute goes from the vapor to goes from gas to liquid. It releases its latent heat, its heat of solution. Liquid gets hotter. So the liquid gets hotter. Liquid gets hotter means solubility decreases. Solubility decreases as the liquid gets hotter. That makes it harder to absorb stuff. It's less soluble. So heat effects hurt again. So heat effects hurt. Heat effects hurt whether I'm absorbing or stripping. That's a general rule. Actually, Le Chatelier would tell you that. Who is this Le Chatelier? Well, he's a Frenchman. Did he have his head chopped off in the Revolution?